but it's been neat work.
I'm gonna step away for 1 minute. I just realized I've got a pen that's not writing here. I'll be right back.
Roger that. Morning, Kevin.
Good morning, Sam. Good morning, Davey.
Greetings. Hey, Kevin. Hi, Sam.
Hey, Dave, how are you doing?
Doing well. John Anderson and I went to sea in some of together in my first 5 trips to the Antarctic. So I had to tune in and see how he was doing.
Oh yeah, well, this is
Hey, Paul.
gonna be a great talk.
Hey, John.
Hey,
Hey,
David, how
there.
you doing?
Doing well. Good to see you.
Good to see you. You looking well?
It has been a while.
You haven't aged as much as I have.
Well, it was a long time ago. We were together on the glacier.
That was the 80s, right?
Oh yeah.
Yeah.
Those were some of my first Antarctic cruises.
Well, those were good days.
Those were good days. That's before the Antarctic was melting.
We didn't even talk about, we didn't even worry about those things. And
No.
of course, now we're completely focused on it. So
Yeah, sure.
you actually were you in Pine Island Bay with us?
No, I was not.
Yeah. I remember we went to Pine Island Bay back in the mid 80s and we didn't even know where the Thwaites Glacier was at that point. It was all about Pine Island because Terry Hughes had predicted even then that was the weak underbelly of the ice sheet.
Yeah.
Terry was way ahead of his time, he
Yeah.
really was. And so we went there and just worked off Pine Island Glacier and took measurements, on the glaciers and all, and never even considered the Thwaites, and it turns out now that's the Doomsday Glacier they've done.
Yeah, sure. Very cool.
Yeah, it's funny how if you're around long enough, you actually see these sort of paradigms come along.
I think you were on the cruise with the glacier where as we steamed back from Palmer Station, we had a leak in the stern, and when they got back to Palmer State, got to Punta Arenas, they filled the place where the leak was with cement.
Yeah.
That's a lot of confidence. It had rusted through apparently to that compartment.
That old ship was wearing down pretty fast. I was on the last cruise, 87.
Oh, really?
It might have been 87, actually. I can't remember. And same thing. We had a hole in the hull and it was flooding one of the aft areas. They had to close it off. So we were just out there doing science with a couple of staterooms flooded, completely flooded.
Man,
Sealed them all.
Yeah.
This is the Coast Guard.
Yeah.
Who do you call when you sink?
if you're in the middle of the Southern Ocean, yeah.
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 We actually had to cross back from, we were in Ross Sea. We had to go back to Punta Arenas. That's about a 10-day steam.
Yeah.
With a belly full of water and the old ship, but it actually was the most seaworthy that ship's ever been, I think.
Well, I guess cement gives you a little bit more ballast than water for what.
Yeah. Yeah, with a round hull, a little extra weight, as long as you stay afloat, can't hurt.
No, it didn't hurt. It helped a lot. And then, of course, we graduated down to the Polar Duke.
Oh, yeah.
It was infamously referred to as the Polar Puke, and for good reasons.
Oh, yeah.
But the Palmer, by the time we got on Palmer, we finally, had a decent ship.
But the Lawrence M. Gould had had stabilizers on the side in order to prevent it from rolling.
Exactly.
And it wasn't in the original design of the ship. It rolled so badly during its tryouts that they had to add the stabilizer so it wouldn't roll.
Yeah. I
Well,
remember
you
that.
know, the thing about the Palmer there, John, is she was made in Louisiana down in Galliano. So that kind of fixed everything up right there. So
I did the initial shakedown cruise on the Palmer out of Fouchon. That was quite an adventure.
yeah, I imagine it was a little bit more rural down there at that time. than
Oh,
it is
yeah,
now.
yeah.
Hey,
Definitely.
hey, John,
Yes.
it's Phil. How you doing?
Oh, hey, Phil.
I was on that shakedown with you as well.
Oh, yeah.
Do you remember we got stuck in the mud and we had to wait for high tide?
I remember that because
So the tide would come up this high.
they built that
Right.
ship in the Schwest shipyard, and they literally had a ditch cut to get it out to the main channel. And so we just, basically, we probably destroyed a few hundred acres of wetlands. Because you could
Couple
just,
extra football fields.
when they cranked that thing up, you could just see waves going out across the wetlands.
Well, Paul, are you ready for us to kick it off?
Yeah, go ahead.
Okay. So I'm going to go ahead and, I'll go ahead and just start off with a share screen. So can everybody see this? See the intro screen? Okay.
Yes.
Okay. So good morning, everybody. My name is Sam Bentley. I'm a coastal and marine geologist and professor of geology at Louisiana State University. And my present day job also involves being vice president for research, but that's of a secondary interest. So as of a few weeks ago, Kevin Shue and I joined on to a team of collaborators to help co-sponsoring this wonderful lecture series that Paul Liu has established. So the present sponsors include NSF, North Carolina State, Louisiana State University, the State Key Laboratory at East China Normal University, and University of Utrecht. So we're all chipping in a little bit, and today it's my great honor to introduce John Anderson for a talk today he's going to give on the late Quaternary evolution on the Texas continental shelf. So before we get into that, I just want to remind everybody that this lecture series has been going on for almost exactly a year now. And during that time, Paul has archived all of the lectures at this YouTube page that there's a link for on this presentation. And it should also be accessible from a link in your a link in the email that comes out weekly with these announcements. So all the talks are available here, and I believe there's also a corresponding web page for a service that's more readily available in China. So Paul can share information on that if needed. Next week's talk is going to be given by Professor Xiaohua Wang from University of North South Wales in Canberra, Australia. The talk will be focused on human impacts on coasts, what has gone right and wrong. So to give a little bit of introduction to John, many of us know him. A number of the folks on this call are former students of John's, former colleagues of John's. I see Phil and Andre and Dave and Davin and a number of folks on the call right now. Well, Dr. Anderson is the emeritus professor from the Maurice Ewing position of oceanography at Rice University and the Department of Earth, Environmental, and Planetary Sciences. And I think many of us recognize that John is quite simply a luminary in marine and continental margin geology. He's been at the job since the early 1970s, been at Rice University since 1975, and he really has led to some remarkable foundational knowledge generally on global climate change at multiple timescales, but specifically, John's something of an iceberg, going back and forth through much of his career between the Gulf of Mexico and Antarctica. So looking at two completely different systems that respond very differently to global climate change. My first, I think my first encounter with John, at least significant one, was at one of the first workshops held for the Source to Sink program back in 1999 at Lake Quinault. And that was organized by NSF with Chuck Nitzrauer as sort of at the head. And I'll never forget this because the talk literally changed my worldview on continental margin evolution. But John's introduction to it was priceless. He stood up and he said, well, Chuck Nitzrauer asked me to give a talk on the global implications of climate change with respect to continental margin stratigraphy. So I'm going to talk about Texas. And it was a great talk. And it really, it used the Texas and Northern Gulf continental margin as a fantastic case study for source to sink processes over a range of temporal scales. So John's had another 22 years since then to do more great work, to pull more ideas together. And so now I'll turn it over to him to give his presentation. And so I'm going to stop sharing, and now I'll turn it over to John, who'll kick on his slides, and we'll go from there. And so as usual, we'll have a few, he'll go through his presentation, and then we'll have Q&A afterwards.
Great. Well, thank you very much, Sam. Can everybody see the screen? I assume we can. Paul, you seeing this?
Yes. Yes.
Okay, great. All right, thank you. Well, Sam's already shown this one, so I'm gonna take you back about, oh gosh, a quarter century here, but I'm gonna build on this story a bit because we've continued to do work in the area. So you might look at this as kind of a history in a way of somebody who's been around a long time and working in the Gulf Coast area. I've always felt that the Gulf of Mexico is a natural laboratory for a number of different things, but for certainly initially we started out really interested in sequence stratigraphy. There are probably a few of you remember what sequence stratigraphy was all about. Almost a thing of the past now, but still very much used. But we started out sort of envisioning the Gulf of Mexico as a natural laboratory in which to test a lot of sequence stratigraphic concepts. And I got to admit, that wasn't my doing. And when Peter Vail came to Rice, when he joined our faculty, I took Peter's class. I think he probably later regretted that because I'm joking, we had a lot of fun and I asked a lot of questions. And so it seemed to me that a lot of these concepts that he talked about could be tested in a quaternary world where you actually knew what sea level was doing, or at least had a fair idea what sea level was doing, and in a place like the Gulf of Mexico. And one of the things I realized early on was that if you look at the Gulf, well, first of all, the Northwestern Gulf has a reasonably high subsidence rate, so that preservation of late quaternary strata is relatively good compared to many areas of the globe. We also have a very strong climate gradient across the region, which is shown here on the right, with precipitation going from about 150 centimeters per year down to a little less than 50 centimeters per year when we hit the Mexican border. So pretty substantial climate gradient. And rivers which pretty much span the global average in terms of sediment discharge, water and sediment discharge. So it's a really good area to work. I'm going to talk about, mostly I'm going to focus on the Western Gulf, but I am going to talk a bit about the Eastern Gulf just to sort of show the contrast there. The time interval I'm going to focus on in the first part of the talk is the interval shown in the sea level curve shown on the left side here, curve A, which is for the last 120,000 years. And that curve is based on oxygen isotope records, global isotopic records. But the dots and the circles there represent actual datums. And there are more of those. This has been updated since I did the slide. So that we're now reasonably confident in this curve as showing generally what sea level was doing over the last 120,000 years, the last glacial eustatic cycle. And we know, for example, that during the last high stand 120,000 years ago, the stage 5E high stand, that sea level in the Gulf of Mexico was about 7 to 8 meters higher than it is today. We have a shoreline that is just about 20 miles south of where I live in Houston, an old paleo shoreline that extends all the way into Louisiana that marks that position. And then as the ice sheets, the Greenland ice sheet, the Northern Hemisphere ice sheets and Southern Hemisphere and Antarctica began to expand, sea level began to fall and ultimately fell 120 meters. But the important thing here is that the nature of that fall was episodic. It wasn't a continuous fall. It was punctuated by a number of up and down cycles of a few tens of meters that reflected these higher frequency Milankovitch cycles that were, of course, driven astronomically. And as we'll see, these were very important in terms of shaping the stratigraphy out on the continental shelf. The curve on the right is the sea level curve. We call it the composite Holocene sea level curve for the Western Gulf of Mexico. It's basically applicable to the Eastern Gulf as well, the entire upper Gulf of Mexico. And it shows the level of detail that we now have on the sea level history for the last, roughly for the Holocene. And you can see it's quite good within a meter or so, a meter or two of resolution. So we're going to start out talking about the longer term evolution of deltaic systems on the shelf, and then we'll work our way into this time frame, which is much better constrained. The data set that I'll be talking about is one that was collected over about a 10-year period in the case of the offshore data, and another 10-year period in the case of onshore data working in the bays. And this slide just shows some of those data sets, and the names here, Banfield, Eccles, Abdullah. These are former students of mine who did their theses, including Phil Bart, you notice in the upper right-hand corner there, who worked on the Perdido Escambia fluvial deltaic system. Other data sets that we've relied on included a data set from Texaco that was collected, a Sparker data set, a data set from LSU that was collected as a part of the Lanyap Delta study, a data set from the University of Alabama that was collected by another of my former students, Lou Bartek, when he was at the University of Alabama. And then I'll mention the Berry Hill data, a very important data set, which really sort of set the stage in South Louisiana, Southwestern Louisiana, and South Texas. So these are all data sets that we've relied on. The vessel you see here is the Lone Star, which was the Rice vessel that we literally bought in a scrapyard and built ourselves essentially for working in offshore work, for taking high resolution seismic data and sediment cores and side scan data. The first half of this talk, the papers are all summarized in this SEPM Special Publication 79. And the idea when we originally set out was that we could use this isotope curve, this proxy sea level curve, in combination with these high resolution seismic data and sequence stratigraphic, to develop a sequence stratigraphic framework for subdividing stratigraphic packages that allowed us to look at deposition through time. And at the bottom here, we see an example of a seismic section that's shown in the map above as that line going from the CV to the BD that stands for Colorado Valley and Brazos Delta. And what it shows are a series of cliniforms, actually two delta packages showing two phases of progradation, one that occurred during marine isotope stage 5A, and the second one that occurred during marine isotope stage 3. And with the surface that separates them, we call it the maximum flood, stage 3 maximum flooding surface. So what we're looking at here is a phase of delta growth during that time interval, and I'll see if I can just use my cursor. So a phase of delta growth that occurred during this time interval. And then when sea level was at its lowest point, there was a transgression that was about 30 meters of transgression that resulted in this transgressive surface that we're seeing here. And then another mode of deposition, which resulted in this stage 3 delta. Now, again, no direct chronostratigraphic control here, but pretty reasonable in terms of how we match the water depths of these packages with the sea level curve. To be able to construct maps like this one that show different deltas through time. And again, the intent here was to look at how stratigraphic architecture varied across the Gulf with different fluvial deltaic systems in particular through this same time interval. And on the right here is just a summary, and I'm not going to go through this, but the point here is that there's a lot of variability when you look across the Gulf of Mexico through this one glacial cycle. And it really leads you to question some of these concepts about when you see shelf margin deltas being produced and when incision takes place to form incised valleys. It varies actually, as you might expect, depending on the size of the fluvial system, the gradient of the shelf, a whole lot of factors. And so that was the sort of the outcome of that work, was to try to demonstrate that, or to at least constrain some of these assumptions that were made in sequence stratigraphy. Now, I'm going to talk just very briefly about the Western Gulf because I want you to understand why we worked so much the Eastern Gulf, why we focused on the Western Gulf. And the reason is because the Eastern Gulf is characterized by relatively low subsidence. When I say Eastern Gulf, I'm talking about the area east of the Mississippi Delta, where subsidence rates are essentially a fraction of what they are in the Western Gulf. And as a result, if you go out onto the shelf, say even mid-shelf depths and take a core, oftentimes you'll core through 1 or 2 meters of Holocene sediments and go right into tertiary age carbonates. So very little subsidence as a result. The shelf is really more of a carbonate ramp. And therefore, we don't get a lot of preservation of Quaternary deposits. And here, this map shows the 3 big fluvial deltaic systems on this eastern shelf: the Alabama Tombigbee, Perdido Blackwater, and Apalachicola Delta. We studied all 3 of these, and I'm going to just use the Apalachicola Delta to kind of give you a feeling for how different this area is from the Western Gulf. And the big difference is if you go over into Florida and Alabama and Georgia, you see a lot of relief. There's a fair amount of relief. And so the drainage map here, which is for the Apalachicola River system, shows this highly complex dendritic drainage system that's draining this area of relief, and it extends virtually to the coast. So no big meandering rivers like we see in the Western Gulf with big, wide, deep valleys that fill with sediments and provide reservoirs for large volumes of sediment during high stands and sea level. And so the map on the right shows our seismic data that we collected in this area. This was a project actually done by my daughter, who did her master's degree with Phil Bart at LSU. She'll talk about inbreeding there. But this was a project looking at the Apalachicola Delta, and it's a pretty spectacular delta when you get out there and look at it. The slide on the right here shows these, if I can find my cursor, there it is. So you see these bathymetric highs that extend out onto the shelf. And actually, that's these features here. They were known to be there. And so with seismic data, we actually see these 2 deltas. This is a dip section, line 13 here, that goes down the axis of one of these deltas, and then a strike section, line 3, that goes across the delta. And we're able to take these data then and construct isopack maps. And of course, in these isopack maps, we can then calculate the volumes of material. And if we know the age of the strata, then we can calculate fluxes, the flux during any given time interval. Now, first of all, the age of these strata, there's essentially no drill core, shallow drill core over on the Florida shelf that allow us to date these deltas. So we're having to infer their ages from their depth distribution. We know that the delta in this case starts at about 60 meters water depth and it extends out to about 90 meters water depth. And again, using the oxygen isotope records, that suggests that this delta is a stage 4 through 3. It represents the stage 3 fall in sea level, which it explains why this system prograded such a distance out onto the shelf. And I'm sure same holds true for this lobe here. So this is the approach we use. And what we see is these deltas have relatively high cliniform angles compared to the Western Gulf. They're characterized by chaotic reflection patterns, very abrupt boundaries between these chaotic reflections and these more laminated reflection patterns that would be associated with, for example, pro-delta deposits, suggesting a fairly distinct facies boundary between the mouth bar sands of the delta and the pro-delta. And so this is basically about what we're able to say about the Western Gulf, is because we only have preservation out there on the outer shelf. Landward of this entire area has been revened during transgression. The deltas have been removed. You can see them pinch out right there. This one pinch out right there. And what we basically have is a transgressive sheet sand, which is referred to as the MOFLA sheet sand, which stands for Mississippi, Florida, Alabama, that covers these, typically covers carbonate, older carbonate deposits. So not a great place to do lake quaternary sequence stratigraphy. That takes us to the Western Gulf, where we've got higher substance rates, allowing preservation even on the inner shelf of quaternary deposits. The other thing that makes the Western Gulf a great laboratory is that we've got abundant platform borings from the oil and gas industry, which includes in many cases cores and logs, gamma logs from these wells. These are collected whenever there's a new oil well being or drilling rig being situated out in the Gulf. They go in, they do these engineering surveys. And we were able to work an arrangement with the oil industry, who funded a lot of our work, and with the companies that acquired these cores to actually acquire these cores. We stored them and we rented a warehouse, and we actually had these cores here at Rice during the time this work was being done. And here's an example in a study area off West Louisiana. All the dots here represent platform boring. So you can see you've got an abundance of data. Now, we don't have cores for all of these. A lot of these, were collected where they just did descriptions, but we have a fair number where we actually had core and were able to do some actual work on the core. And this just shows how useful these data are, where you can actually correlate seismic facies with lithofacies. Here we've got two platform borings, and we see this fairly distinctive chaotic unit, chaotic seismic character in this upper unit with a lot of cut and fill structures, what we've interpreted as a distributary mouth bar deposit, down cutting into pro-delta silts and clays, which is supported by the platform borings. Now, we're also able to take these cores and do some chronostratigraphic analysis. So we are able to take our seismic records where we've already identified what we believe to be the key surfaces, like the stage 2 low stand surface, the stage 3 maximum flooding surface, the stage 5E maximum. And then we can look at a core, in this case, core B2 here, and do oxygen isotopes. Now, a lot of people feel like, well, you can't do oxygen isotopes in shallow water. Well, you can if you have a good seismic stratigraphic framework. Now, of course, when sea level is low, you don't get, the forams, the calcareous forams you need to do this type of analysis. But for certainly when the shelf is flooded, you can actually, here's 5E, for example. This would be the stage 5E maximum flooding surface, a time when the shelf is fully flooded. And you see this curve looks pretty good, like a typical spec map for the oxygen isotopes. And then when you get into the shallower water, see, it starts to, sometimes it starts to get a little more obscure. But we also, working with Dr. Martin Legault, my colleague who sadly passed away not long after this study was completed, Martin and his students looked at forams in these cores and did paleobathymetry looking at the forams, things as simple as, percentage of planktonics, but also looking at species level identification to reconstruct paleobathymetry. And so using those combined data, we were able to develop what we felt was a reasonably good chronostratigraphic framework that allowed us to actually identify when these different deltaic packages were formed. And this map on the left here shows the sort of the result of that work from the Western Gulf with the deltas. The numbers here are the stage, the oxygen isotope stage. So here's the oxygen isotope stage 5E delta. The 5E shoreline comes right through here. And as sea level fell during this time interval, the delta prograded out to approximately 50 meters water depths. And then it backstepped. And that was during this transgressive event. And then it prograded back out again, what we call the 5C delta. And then again, it backstepped during this transgression, and then it prograded again. So what we're seeing here is for each of these river systems, this is the Brazos River Delta, this is the Colorado River Delta, this is the Rio Grande Delta. This is what's we refer to as the Western Louisiana Delta, which we think may well be the Red River, which might have been separate from the Mississippi at that time. And then the Mississippi, we even see at least one lobe of the Mississippi during this time. And so we can see how these deltas prograded seaward as sea level was episodically falling, stepped landward during these transgressions, and then would prograde back out again. And with each cycle, roughly 20,000 year cycles, again, Milankovitch driven cycles, representing about 20 to 30 meters on average of sea level variability, a delta builds out and then it gets transgressed. And when that transgression occurs, you ravine the top of that delta and that sediment goes into the next delta. And so this recycling that takes place as sea level is rising and falling during episodic sea level rise and fall results in a situation where each cycle results in a bit more sediment being added to the package. Now, I should mention that we did some collaborative work with folks at Utrecht, George Postma, many of you know, and one of his students, Van Heist, who did his PhD dissertation looking at the Colorado Delta system, where we had these kinds of volumetric constraints and trying to actually model the behavior of the system to explain this mode of growth that I've just described, sort of a fill and purge type cycle. And I'm not going to have time to go into that, so I'll put the whole reference here in case you want to try to look at that. But just some examples. We do volumetric estimates of the deltas using maps like this one, these isopac maps. And then knowing the time frame, we're actually able to calculate the volumetric accumulation rate, the VAR flux. And this just shows some examples of these increases I was talking about. In the case of Brazos, you can see that the kiloyear flux goes from 1.10 cubic kilometers per kiloyear in the initial phase, and then the 1.35 slight increase. But by MIS3, it's virtually tripled. It's almost tripled the volume of sediments. So the question then, is, well, is this because there's an increase in drainage, climatically driven? I don't think so. I think we're looking mainly at recycling those sediments during these up and down sea level fluctuations. Now, obviously, the climate is, as we're going into the glaciation, the climate is getting wetter. And so there must be some component of climate-driven increased sediment supply, but it's a little hard to separate those out. You see a similar situation with the Colorado Delta here, where the MIS3 delta, the volume changes again into the low stand delta is essentially an order of magnitude. So that by the time we get into the low stand, we're looking at these big shelf margin deltas, which are written about quite a bit back in the 90s. These are largely, I think, products of recycling of sediments off the continental shelf. And so that would be and they have different ages, I might add. When these low stand, they're called low stand deltas, probably not a good term. I like shelf margin, because we find that some of these features were active from stage 3 right on into the initial transgression. Other ones began forming earlier or later, depending on the size of the fluvial system that was feeding it. During stage 2 time, when the shelf was exposed, this is what the shelf looked like. This is a digital elevation map constructed by Alex Sims, showing what the shelf would have looked like during stage 2 time when it was fully exposed and you had these deep valleys that it would extend across the shelf. Now, interestingly enough, I think one of the most interesting things we found was that even during transgression, we get these large fluvial dominated deltas on the continental shelf. And that includes the Colorado River, the Brazos River, and the Rio Grande River. Yes, even the Rio Grande River produced a sizable delta during the transgression. And if we look at the location of that delta and its depth distribution, the indication is that it was active sometime in the late Pleistocene, right on up into the early Holocene. How do we know it's transgressive delta? Well, again, this surface, SP2, stands for sequence boundary 2. And that's that surface you see that this digital elevation map showing here. So we've compiled, Alex Sims compiled all these data to map that low stand sequence boundary. That's that surface there. So this delta clearly sits above that delta, meaning it's post stage 2 low stand. And you can actually see the cliniforms here, and you can see variations in the angles of those cliniforms, which is due to the fact that reflects lobe shifting as this delta is prograding. And so, and that's also reflected by this isopac maps of the delta. So even during a period of rapid transgression, and this was a time when sea level was rising at 5 to 10 millimeters per year, there were deltas formed. Now in this case, this clearly has to be climate, because sea level is actually rising. And but we know the climate in Texas was fairly wet during this time interval. It's also related to purging of sediments from the catchment areas, such as in the case of the Rio Grande, when there was a lot of denudation taking place within the Rio Grande trough to feed these sediments out into the shelf, onto the shelf. Colorado River, here's another example of a system that we see this. This is an isopac map of this, again, late Pleistocene, Holocene transgressive delta. And you can see the outer part of this delta looks very much lobate in shape. You can imagine the feeder valley here with a bunch of distributaries. And then as the delta began to retreat landward, actually as sea level was decreasing in its rate of rise, it took on a more strike orient, shore parallel orientation, suggesting more of a wave dominated type system, which is similar to what we see in the Rio Grande as well. So these transgressive deltas have to reflect the role of climate in overcoming even a relatively rapid rise in sea level to produce deltas by rivers that are today fairly small sediment fluxes. Now, at the time these deltas were retreating landward, one of my other I got a student by the name of Patrick Taha did a study of the Brazos and the Colorado valleys on shore, building on work of others, and including people like Mike Blum and some of his colleagues, to see what was happening within the onshore valley. And what we see is that at the time those offshore deltas were active, aggradation within the onshore valleys was fairly small, but then it doubled at the time these deltas were abandoned, suggesting that the locus of deposition actually shifted landward and began to fill this big low stand incision that was created by the Brazos and the Colorado River. So today, very different story. We have the Colorado Brazos together form a delta headland that's highly wave reworked. Same way with the Rio Grande. You can virtually walk across the mouth of the Rio Grande River today. And the Brazos River, another example, wave-dominated delta that's actually the size of this delta is even larger than it normally would be because the river was diverted by the Corps of Engineers back in 1929, and all the delta was eroded here, and that sand helped to construct this delta. The finale for this is the deposition of what's referred to as the Texas mud blanket, which is a vast blanket of mud which covers particularly the central Texas shelf, but it extends over in East Texas. This is as much as 50 meters of Holocene mud draping the outer shelf. And you can see that here's the ancestral Colorado Delta. You can see that mud onlapping that delta in the same way in the Rio Grande. The delta is here. I'm sorry, there's the delta, and here's the mud onlap. And what really surprised us was that when we looked at some of the platform borings within the Rio Grande Delta, we found that the accumulation of that delta occurred dominantly just in the last 4,000 years. That's about 170 cubic kilometers of sediment, most of which, based on the mineralogy, came from the Mississippi River. So very significant change in sediment distribution that took place at this time, probably related to some oceanographic changes, some changes in surface current circulation patterns, which today bring sediments from the Mississippi River over into this area, into Texas. And we think that system really got active during the late Holocene and buried these offshore deltas. And since that time, they've been inactive. Now, excuse me. So the last part of the story here has to do with the rivers that were really never large enough to fill their valleys and produce large delta systems out on the shelf, but that still contain an important record of what sea level and climate is doing in terms of how it's regulating delta development and river discharge and fluxes at a time when, remember, we have a fairly accurate sea level curve, and quite considerably more accurate than what we have for the 120,000 to 10,000 year period. So the work I'll be talking about next is published in a GSA special publication. We sort of shifted from our offshore research vessel into a drilling barge, which was an adventure within itself. And we began looking at bays across this climate gradient, starting with Mobile Bay and ending up in Baffin Bay, across this broad climate gradient. And these are the bays that were studied. Apalachicola Bay was subsequently studied by the USGS, and but I won't talk about Mobile or Baffin today. Now, our first work was actually using our offshore data, we recognized that the Trinity Valley here, which is now occupied by Galveston Bay and splits into what's called the Sabine Valley, which is occupied by another estuary, Sabine Lake, that valley was occupied by initially fluvial deposits, and then the sea level rose. These fluvial deposits were replaced by Bayhead Delta deposits, and as sea level continued to rise, Middle Bay, and then eventually tidal deposits as the shoreline stepped through the area. This map is from a student, Mark Thomas's work back in the early 90s, and it shows the sort of backstepping nature or landward stepping nature of these Bayhead deltas, which are numbered here with 1, 2, 3, and 4, and the same deltas here by correlation, how these deltas stepped landward as sea level was rising. And you certainly get the impression that they are in fact stepping landward. They're not migrating landward. This is a backstepping kind of character. You get that same impression when you look at tidal deposits, which are shown with Roman numerals here, which are very distinctive, as are the tidal delta deposits, which are, I'm sorry, the Bayhead Delta, which do in fact show very low angle cliniforms. But the most distinctive facies are the tidal facies, which are characterized by these high angle bed forms that reflect, tidal incision and backfilling of tidal channels and deltas. And what you see is that these tidal inlet deposits sort of appear again to step backwards. There are none between. So these represent backstepping shorelines, which we now know are connected to what were barrier islands like Hill Bank, for example, and Shepherd Bank and Sabine Bank. So at this time, sea level, if we look at what sea level is doing, this is the time interval we're talking about, the early Holocene. And every indication in the sea level records is that sea level was coming up episodically around this time. And why not? I mean, we know from our studies of ice sheets that ice sheets do not retreat steadily and uniformly. They're grounded on different, out on the continental shelf at different water depths. They're experiencing different climate forcing between northern hemisphere. So we know that the northern hemisphere and southern hemisphere ice sheets retreated in an episodic fashion. And so it's not surprising to see that sea level rose in an episodic fashion, and that the magnitude of these rises was on the order of several meters, enough to cause some of these backstepping events that we're observing offshore. Now, in order to really get a better feeling for how this is affecting these fluvial system, Bayhead Delta systems, we elected to move into the bays where, given the calmer waters, we were actually able to shoot, higher resolution seismics and actually collect drill core from our little drill barge. And so we began this project, and I'm just going to show a couple of examples here quickly. Galveston Bay, which here we have a map showing the a structure map showing the valley occupied by Galveston Bay. And I need to point out that this is based on earlier work done back in the 70s by the USGS, where they went in and did very detailed studies of these bays using sparker systems, which are not very good for giving you real details like we see in this uniboom line here. But they image this Pleistocene, Holocene surface very nicely, allowing us to map these valleys and select where to put our cores. And so the next objective was to come in and collect unibeam data, which are shown here. These are the USGS data. These are our data, which are better quality data, higher resolution data that actually allow us to see much better detail to do seismic facies analysis. We can see terraces along the flanks of these valleys, and how, as the valley was being flooded, it was being flooding history was influenced by these terraces. And so the object now is to identify these flooding surfaces in these sections, and then using a line that's collected right at the axis of the valley, which is this line here, to collect a series of drill cores shown with the stars that allow us to date these backstepping sequences of paleo environments within these valleys. This is a dip section from the Trinity River to offshore Galveston, showing about 30 meters of stratigraphic section here. And so what we're able to do is actually drill through these backstepping sequences. Now the olive green here, that's the Bayhead Delta. And you see times when the Delta was aggrading, there's claniforms here. The Delta stabilized at this time, and then it appears to have stepped landward about 20 kilometers or so within what appears to be a fairly abrupt period of time. And there are a number of these flooding surfaces we refer to. And those surfaces, now that we have drill core, we're able to go in and do radiocarbon dating to try to constrain the timing of those surfaces. And I'll show you the results from that in a minute. But as you can see, some very dramatic, in fact, during the time this 7,700 year flooding surface was formed, the Trinity Bayhead Delta was backstepping, was retreating landward at a rate of about kilometers per century. So in a lifetime, you would have observed, if you lived in this area, you would observe that backstepping character. Now we can take these data and we can reconstruct paleogeographic maps. And again, the olive green here shows the Bayhead Deltas. At this time, 9,600 years ago, it was a fluvial valley. Right after that, it began the first flooding event, formed the Bayhead Delta, et cetera, et cetera. And by 7,300, the Delta or the valley was completely flooded. Corpus Christi Bay represents another example of these I'll show, where more arid type conditions. Here's the valley, here's our data set. And here's the section. And what it's showing here is a rather different scenario where we're still seeing some backstepping, but a much more aggradational character. Even the barrier island, in this case, Mustang Island, is an aggradational barrier. So this is a reflection of the relief in this area, which is steeper, both onshore and offshore. So the shoreline was more stabilized as it came up. And it took larger magnitude sea level events to manifest themselves in the stratigraphic record, but they are still there. Now, if we take those combined data from all the different valleys that we've worked, and we plot the distance that the Bayhead Delta shifts landward, that'd be that distance there, and the age, based on our radiocarbon dates, what we see is that around, during the early Holocene, during this period of time here, these flooding surfaces appear to be contemporaneous, certainly within the uncertainty of radiocarbon dating. And in fact, this event, the biggest event, is the 8,200 year event, which has been written about. That's a global event. Tor Tornquist wrote about this and its importance in the Gulf of Mexico and globally. It's the Lake Agassiz draining event that caused sea level to rise. But the interesting thing is sea level only rose a meter or two to cause this dramatic event that is manifest in itself in the backstepping of these Bayhead Deltas across the entire Gulf of Mexico, just a couple of meters perhaps. Following around 7,000 years ago, there are still flooding events, some quite significant, but they don't correlate. That suggests that during this time interval, sea level was dominating the Bayhead Deltas and their behavior, whereas during the middle late Holocene, climate was dominating the signal. A good example of that is Baffin Bay, which is the southernmost estuary in the system. And actually around 5,500 years ago, up until that time, Baffin Bay was much like the other bays of the Gulf Coast. It had a big bayhead delta system. At times it prograded and retrograded. It experienced similar flooding events. There's that 8.2 kiloyear flooding event that the other rivers. So it's sort of similar in many ways to the other bays, I'm sorry, in the area. And then after 5,500, suddenly it changed dramatically. The Bayhead Delta, this is actually not a Bayhead Delta, it's more of an upper bay facies in this case. There were things like worm tube reefs and oolites, and it became an arid system, hypersaline bay lagoon system. And that's a very dramatic event that took place at 5,500 years ago at this location, but not at other locations. Because again, remember this climate gradient and this precipitation gradient that we have across the region. And so the map on the left, or the figure on the left here, just shows a generalized paleo climate record for the Holocene for Texas. And what we know from this and other work is that in general, the early Holocene was marked by cool, wet conditions, shown in black here. And that by late Holocene time, conditions became more arid, occasionally reverting back to wetter conditions in some locations, but not others. So we see a kind of a varied history depending on the location. That means that to actually understand what's going on here, we go to the individual bays. Here, for example, in this case, we teamed up with Sophie Warney and one of her students at LSU, who's did palynology on cores from Trinity Bay, Galveston Bay, I'm sorry, and Corpus Christi Bay. In this case, you can see that the shift to more arid conditions in the case of Corpus Bay took place around 8,000 early Holocene time, but that same, and then again around 6,000 years ago, but that it was much later further to the north up in Galveston Bay. So these things begin to make sense, these changes, these climatically driven changes in the configuration of these bayhead deltas and their sudden demise as they step landward begin to make sense, but only when we begin to look at individual systems, because the climate is so complex here in Texas. The gradient is so complex. And added to that, we've got, the size of the drainage basin. Even these fluvial terraces that I showed earlier control to some degree the flooding history of individual bays, as we've pointed out in various papers. So, this is unfortunately where I kind of I'm running out of steam, both in terms of the talk and in terms of the research. But I think there's a lot to be learned here by continuing this work, by looking at how these different deltaic systems responded to climate. I think it makes sense that these bayhead deltas are going to be excellent locations to look for climate records. And I think this work demonstrated that that is indeed the case, that we are seeing, in fact, some interesting climate change and associated change in bayhead deltas. Now, to put all this in context, and I'll just show the conclusions here so you can read them, but I want to make a couple of points. I won't go through the first set of conclusions, but I want to end up talking about the last few. The current rate of sea level rise in the Gulf of Mexico is approximately 4 millimeters per year. The natural rate of sea level rise up until about a few centuries ago was 0.5 millimeters per year. So there is no question, based on current sea level estimates from tide gauge records and satellite records, that the rate of sea level rise in the Gulf of Mexico has accelerated almost tenfold, eightfold in the last 2 centuries. The scary part is that this 4 millimeters per year is taking us back to the early Holocene. So we've now reverted back to the Holocene in just 2 centuries due to human activities, global warming, and the acceleration of sea level rise. And as I pointed out, that was a time when conditions were very different. And when these bayhead deltas were very, very sensitive to any change in sediment supply. Had to have been. Although we can't tease out those sediment supply versus sea level differences. We know that these rates we're approaching now are approaching the rates that are being measured for what are called vertical accretion rates for coastal wetlands in the Gulf of Mexico, which are in the range of 5 to 10 millimeters per year. So that suggests that in the next few decades, we will cross that threshold of vertical aggradation. And we all get asked by people, I'm sure, so what's the big deal about a 1 or 2 millimeter per year sea level rise? I mean, that's hardly noticeable. Well, again, this is not an insignificant amount of rise when you're talking about vertical aggradation rates of the delta plains of these bayhead deltas. And we're at the tipping point now for when we will begin to see that change. We've already crossed that tipping point in large areas of Louisiana. And so we're seeing rapid changes in coastal wetlands loss in Louisiana. We're at the tipping point now for these bayhead deltas. And again, we'll likely cross that threshold pretty soon. The other thing I want to point out is that most climate models for Texas indicate that we're going to experience increased aridity throughout the state, and including Western Louisiana, probably over the next several decades. That's likely going to result in a decrease in sediment supply coupled with an increase in rate of sea level rise. It doesn't look good for the bayhead deltas of the Gulf Coast. So I'm going to stop there, and I want to acknowledge my colleagues and former students who have all participated. I hope I haven't left anybody out here, but all participated significantly in collecting this data set and in interpreting these data. Thank you very much.
John, thank you very much. That was great. We have time for a few questions. If folks want to turn their cameras back on and start a dialogue. Phil. Unmute, Dr. Bart.
Okay. Nice talk, John. So I guess, man, it made me think of many things, but I guess one thing I was kind of curious about is what you're feeling about what these results from the Gulf Coast say about Mitch Rovika's words about, GIA kind of effects and their variability. Are you seeing something that's kind of parallel with the sorts of things he predicts about the variability of sea level?
Well, of course, we know that subsidence, even along the Gulf Coast, varies from 1/10 of a millimeter per year, fraction of a millimeter per year in Florida, Alabama, places like that, to 10 to 20 millimeters per year, fastest rates in South Louisiana. Actually, in Texas, we're seeing some pretty high rates as well. We're seeing rates as high as 4 or 5 millimeters per year. Those rates actually occur in the incised valleys where we have these thick Holocene sediments that are compacting. And as we know from work about Tornquist and others, that's really the driver in sediment compaction. It turns out all our tide gauge records in Texas are in bays, which are in incised valleys. So we had this very biased record here of what sea level is doing, but it certainly suggests that the rate of rise is increasing, but it's also showing a lot of variability, which suggests that things other than eustatic rise and even maybe sediment compaction are contributing. Whether GIA, this is debatable. I think there are a lot of people that argue that, well, GIA effects are only measurable in places like South Louisiana. But I think we may actually really want to question that. And like you say, based on some of Mitrovica and others' work, suggestions at least that there may be some at least subtle contributions to sea level rise and fall. One of our most southerly, the only wet tide gauge record we have in Texas is in South Texas, in an area pretty far removed from Insight Valley. Actually shows an anomalously high subsidence rates. So, you know, there are some unknowns here, and GIA could be part of it.
Great,
Thanks, Tom.
thanks. Who else? Kevin.
Thank you. Dr. Anderson, this is an excellent talk. I have one comment and one question. So when you present the information for the Northern Gulf of Mexico, I was thinking about East China Sea and the Yellow Sea. And I realized there are lots of similarities. So lots of papers have been talking about the Paleo Yellow River, Paleo Yangtze River, where they were during late Pleistocene period on the East China Sea and Yellow Sea. And I believe similar work can be done in multiple ocean margins. And so that's one comment. I also have one question. So in your slide, you showed a large mud deposit on the Texas shelf. I believe you call that as a Texas mud patch or mud blanket.
Right.
So if the mud is mainly from the Mississippi River, including the main Mississippi, Red River, or whatever, Atchafalaya, whatever you call it, what would be the driving mechanism to deliver such large amount of mud to the Texas shelf? And people have been studying mud deposit over many years, and normally, if there's a large mud deposit, they should be continuous. So based on your data, if it's an isolated mud patch, what would be the driving mechanism to separate from other mud deposit?
Great question. Thank you, Kevin. Yes, with regard to the Texas mud blanket, two parts to that question. One is, you know, why do we suddenly see this increase? And part of that, of course, has to do with the fact that we flood the shelf, you know, the inner shelf during this time interval. I think the explanation, at least the one that we've offered in the paper, and we published this in the paper in JSR some years ago, I think 2010, one of my students, Robert Waite, was the first author on that paper. If you drop me an email, I can send you a PDF. But what we suggested there was that this represented a paleoceanographic change, because at least today, sediments are being delivered, significant volumes of sediment are being delivered from the Mississippi, mouth of the Mississippi River down into Texas. And that's why our waters are so muddy in Texas. And so what we suggest is that a paleoceanographic change resulted in these longshore east to west currents and west to south currents, increase in those, the capacity of those currents to actually deliver that mud to the central, mainly to the central Texas shelf. Why the central Texas shelf? Well, if you look at a bathymetric map rather of the central Texas shelf, it's actually a bathymetric embayment. And it's a bathymetric embayment because that's an area where there are no rivers flowing into the Gulf. So in these other deltas, the Brazos, the Colorado, and the Rio Grande, were filling accommodation, keeping the shelf fairly high. The area in between the central Texas shelf with no significant rivers was sediment starved. So there are no deltas there. And so what we've got is an embayment in the shelf, and that's where these muds are accumulating. They accumulate outside the embayment. So the Texas mud blanket extends all the way into East Texas and converges with the what would be probably the Louisiana mud blanket. But it's thickest in this embayment, and that's just due to the accommodation space created by this bathymetric load.
Well, I think we got time for about one more question. Anyone?
Hey, John.
Paul?
Hey, Paul?
Yeah. Hey, John, great talk. So following Kevin's question, my question is, is that kind of, based on what you said, the longshore circulation from east to the west is kind of reconstructed or initiate around 4,000 years? If that mud blanket kind of show dominate starting about 4,000 years ago. So the sea level high stand, then we gradually form that kind of anti-clockwise circulation in Gulf of Mexico.
That's our argument in this JSR paper. Now, I would add to that, and of course, lobe shifting, could be another factor but we thought about that and we looked at the mud blanket. If you go and look at the JSR paper, you'll see that we have a number of long cores that penetrate the mud blanket, and that we sample those cores at fairly high resolution and did quite a bit of radiocarbon age dating. So the chronostratigraphy for the evolution of the mud blanket is pretty robust. We actually expected to see cycles. We expected it to be much older than it was, first of all. And we expected to even see lobe shifting within the Mississippi Delta, perhaps, as it would shift from eastern lobes over to more western lobes. We don't see that. If you look at the data on the paper, you'll see that actually any lobe shifting sort of gets, filtered out in the accumulation of the mud blanket. So the only explanation, we ruled that one out. We could not see any evidence that discharge sediment flux at that time for the Mississippi River had significantly increased in the late Holocene time. And so again, it was sort of a fallback position here that we said, well, we know that today this mud is being dispersed by these, longshore shelf currents that move from east to west under the prevailing southeasterly winds. And that this reflects sort of maturing of that oceanographic coastal circulation system that's yielding more mud from the Mississippi. I should also add that it's not all Mississippi. There is a Brazos component, and of course there's a Colorado component, but it's dominantly Mississippi mud.
Very good. I mean, what's the average thickness of that mud blanket? 10 meter?
50.
50 meter.
50 meters of late Holocene mud.
That's very good. Actually, this is also, as Kevin pointed out, it is also true in East China Sea, Yellow Sea, even of the Mekong. We found that longshore sediment transport, we name it called the Distal Depot Center. It's also up to 30 to 50, 60 meters. That's something that very common. Very good. Thank you.
Yeah, we see mud blankets in other locations. I know Chuck Netrauer and his students work, offshore Brazil and the Amazon mud blanket. So this is not uncommon of type of feature by any means.
Thank you.
Well, I think we're gonna end there, as long as the senior MC is Paul Liu okays it. You good, Paul?
Well, you are the boss today.
Okay. Well, everybody, thank you, and we wish everyone a good morning, midday, and afternoon. I want to quickly put back up presentation for next week. Professor Wong, don't miss it. Be there, and we'll see you then. Thank you all very much, and have a very source to sink week.
Thanks, John. Take care.
Thanks. Good talking to you, David.
Yeah.
Nice talk, John. Been a long time.
Thank you. Who was that?
Mike Steckler.
Oh, hi, Mike.
Thank you, Anderson and Paulio, Professor Paulio.
How you doing?
Thanks, John. That was a good talk.
Thank you very much.